Right guys, so today we're going looking at cation exchange from the chemical properties of soil chapter. Okay, so cation exchange is our ability for our soils, clay and humus to attract, retain and release cations. Okay, so cations are positively charged ions such as your hydrogen, your potassium, your calcium ions. So any ions that are positively charged are going to be known as cations. Why are cations attracted to soil? Okay, so your small clay particles are going to be negatively charged. So we see all our negative charges on the surface of our clay soil particles here, and that is why our cations are attracted to them. Okay, our clay soil is going to be an awful lot better at our cation exchange due to the surface area seen in this diagram here. So as we can see, we have loads of small clay particles, loads of area for more cations to attach to the clay particles, rather than our sandy soils who have a larger surface area, larger soil particles, and less cations are going to be able to attach to that surface. Okay, so moving on, so our positively charged cations are attracted to negatively charged humus and clay particles. This prevents leaching. Okay, so our leaching is going to be seen in our podzol soils. Okay, so again, our positively charged ions are going to be attracted to our negatively charged soil particles. Soil colloids, which are the smallest particles that exist in soil, are the most chemically active and have the highest rate of cation exchange. So what can we take from that? The smaller the particle, the greater the cation exchange. Cations are released from the soil through weathering and removed from the soil solution by plant roots. Okay, cations with two positive charges such as calcium here, Ca2+, can remove two cations with one positive charge each, okay, such as your potassium. So to explain that, we have our calcium coming in here, Ca2+, and that removes two ions with a +1 charge. Okay, so +1 plus +1 is going to equal our +2, and that is why our +2 for our calcium is able to replace those. Okay, so if we have two positively charged potassium ions attached to our clay particle, if our calcium comes in, that's going to remove two of our potassiums. So this is going to be particularly useful when we're talking about liming. Okay, that's going to remove our acidic hydrogen ions. Okay, so that's where that's going to be very useful. All right, clay soils have better cation exchange, as we mentioned before, than our sandy soils, and the three reasons for that is that they have smaller particles, they're negatively charged, and they have a larger surface area. More ions or cations are going to be able to be absorbed on each of the clay particles in comparison to our sandy soil, who are going to be able to absorb less cations. This table over here can be quite useful. Sometimes you're asked to estimate what is the cation exchange capacity of a sandy soil, a loam soil, a clay soil. There's loads of different types in the book, but I think these are the three most important. So here we can see the cation range for sandy soil is 1 to 5 in comparison to our clay, which is 30 to 50. So our clay soil is almost 10 times better at exchanging cations than our sandy soil. And our loam soil is going to be bang in the middle, give or take 5 to 15. Just a reminder of what our loam soil is there's equal amounts of sand, silt and clay. And then we go on to our new definition here, which is our cation exchange capacity. So hopefully you can remember that our cation exchange is the ability of a soil to attract, retain and release cations. Our cation exchange capacity is just the quantity of cations a soil can absorb. So this can be described as the capacity of soil to exchange cations between the soil surfaces and soil solution. Okay, so again, if we have a positively charged cation such as our calcium 2+ coming in, that is going to remove two negative ions. Main example of our cation exchange is in liming. Okay, so liming is where our calcium and magnesium ions, both basic ions, replace the aluminium and hydrogen acidic ions through the process of cation exchange. So here, liming, the main reason we lime our land is to raise the soil's pH, okay, up to that ideal of 6.5. So we are adding in our basic ions here, our calcium and our magnesium, and we're replacing them with our acidic ions, hydrogen and aluminium. So hopefully you will notice that our calcium 2 plus and our magnesium 2 plus replaces, that is 4 plus in total, replaces our hydrogen, which is +1, and our aluminium, which is +3, and that's also 4 plus. Okay, so everything is going to balance out. Our calcium and magnesium move into the soil, our hydrogen and aluminium move out of the soil, increase our soil pH to that, hopefully closer to 6.5, and get better nutrient availability for our soil. So here are some of the importance or the advantages of spreading lime. So it neutralizes acidic conditions, crops grow better, promotes flocculation, promotes earthworm activity, which is going to improve the drainage, the aeration, the structure, the organic matter of your soil. Bacteria benefits, so hopefully encourage more rhizobium bacteria for your clover. More clover grows, which fixes nitrogen from the atmosphere. That means you need less fertilizer, lower your cost, increase your profit. Less parasites in animals, so less liver fluke, which are known as an endoparasite. Helps animals' bone formation naturally because of the calcium. Them bones need calcium. And improves your nutrient availability. So your nutrients are going to be more available the closer you get to your 6.5, your 6.5 pH. Okay? Factors that affect your cation exchange is your humus content, your clay content, your soil texture, and your pH. So how do they affect your cation exchange? Typically, you're going to be asked to explain or name and explain 2 of these. So hopefully if we go through the 4 of them, you'll remember 2 of them. So our humus content. So humus has the highest rate of cation exchange value, as the colloidal humus has the highest amount of negative charges. The more negative charges the soil particle has, the more cations it's going to be able to attract. So humus has 30 times more effective than our clay particle, which earlier we saw that was nearly 30 times more effective than our sand particles. Clay content. So soils have a high clay content are naturally going to have a higher cation exchange capacity due to being a smaller particle or a smaller soil particle. Our soil texture, so soils with finer texture are going to have a higher rate of cation exchange, again because of the clay content. And our pH, less cations are going to be available at lower pHs of 5 and less than 5. So if we can increase our pH by spreading lime, increasing the amount of calcium and magnesium ions in our soil, liming is going to increase the amount of negative charges in our soil colloids, and that is going to increase our cation exchange capacity. To our experiment, okay, so this is a common experiment that can be asked to draw a label diagram and explain the results or whatever. Okay, so step 1, we're going to set up our apparatus as shown. So we have our funnel, we have our filter paper, our retort stand, and we have our beaker here to collect our leachate. Add 5 grams of sieved dry soil to your filter funnel. Okay, so we add our soil into our filter funnel that has our filter paper in it. And with a dropper, we are going to add potassium chloride to the soil drop by drop. So KCl, potassium chloride, is being added to the soil. And we are going to collect our leachate or our solution in our beaker. Okay, how we're going to test the leachate for calcium, we're going to get our beaker, pour it into our graduated cylinder and add 10 drops of ammonium oxalate to the leachate. So we have 2 key chemicals. We have our potassium chloride pass through our soil, and then we're going to test our soil with our ammonium oxalate, and that's going to test for calcium. To get a white precipitate, calcium is present. Okay, so hopefully our calcium is going to be present. And we're going to repeat this experiment until we have removed the calcium ions from the soil and replaced them with potassium ions. So we're going to keep repeating this experiment until the calcium is removed, there's no white precipitate, and potassium ions have moved into the soil and removed the calcium ions. Okay? So that is everything I feel that you need to know for cation exchange capacity, the factors that affect cation exchange, and the experiment to go with it. On these videos, just go to Mr. Ag Science on YouTube or check out the website or Instagram page for more. Thank you.